in my project, I also analyzed the use of high-level languages for parallel programming. And this is particularly attractive for scientists because the higher the programming languages level, the easier it is for the programmer to develop programs, and therefore the less time it's been taken to finish writing those programs. Now, most parallel applications are written in cryptic, low-level languages like C and Fortran. This is because it's difficult and complicated to achieve processor intercommunication. But the advantage to Python is that it has a module, or several modules actually, that were written in C but are implemented in Python that can achieve that processor communication. So this allows a scientific programmer to use this high-level language and allow him to avoid the use of ugly languages like C and Fortran. So, my hypothesis was that the BSP model implemented in Python would allow a scientific programmer to easily write efficient and scalable algorithms, but still within a short development time. What I mean by scalable is that for each processor that we add to the resource pool, we should see a corresponding increase in execution speed. So basically what this means is that if we have 3 processors, then ideally the program would execute 3 times as fast as if we only had 1 processor. Now in practice this is never going to happen because there is some amount of overhead due to communication. But in order to be feasible, a parallel algorithm has to be at least somewhat scalable. And so to test a BSP model, I brought it back to the heat equation that I described to you earlier, and I built a parallel application, I built a parallel application from the ground up, and I designed it to be scalable in such a way that at runtime the program would analyze the size of the grid and distribute it among the various processors so that no matter how many processors there were, the program would be able to utilize all of the resource pool effectively. And so then to analyze the scalability, I tested the program first with only 1 processor as the control, then with 2 processors with 4, 8, and all the way up to 32. And then you can see my results on this chart. Now, this pink line is the ideal scalability. That is for each processor that I add, its speed is utilized to 100%. And then this lower line here, which is supposed to be blue, is the data that I obtained experimentally. And as you can see, even with a large resource pool at up to 32 processors, this program was actually about 72% efficient, which is still a significant performance gain. And considering my lack of experience as a parallel programmer, it probably could be even closer to that pink line if the real computer programmers knew what they were doing and helped me out with this. And so in conclusion, it became clear that using the BSP model implemented in Python, parallel algorithms could easily be developed by scientists, but still developed in a short amount of time. And this is useful really for anybody at NASA that wants to run any type of complex simulation or do calculations with large amounts of data, because they can easily write parallel algorithms that can take advantage of the extra power available in parallel environments, but without having to know all the nitty-gritty about ugly languages like C and Fortran. So that concludes my presentation, so I'll open the floor to any questions.
Did you ever run it more than 32 nodes? Did you ever get that?
Sorry, I did, but it got to the point where that line started to drop off a little bit, and it had to do with the fact that communication was becoming a bottleneck. And so when I got more, as I added more processors, they were dropping off in there in the amount of gain that I was getting, because there was more communication going on than there was actual computation.
Were you using the InfiniBand or the regular?
Using the InfiniBand, yeah.
So your experimental codes are ready to do variable grids, and then you can distribute to various processes while you run variable size grids.
Yeah, I'm not sure what you're asking now.
Your experimental scheme that you have here is
Oh.
it ready to do variable size grids? And,
Oh, yeah.
and then when you do that, you would distribute to various clusters.
Exactly. At runtime, the program would basically divide the grid into an equal piece for each processor. So if there were 3 processors, we would just divide it into thirds, or at least as closely as it could.
So how big of a grid did you have?
The particular one that I used for this data was 5,000 elements long and 500 wide. And the reason for this, the reason that it was a really long rectangle was because as the grid got taller, so to speak, as the y coordinate got larger, there had to be more and more communication in between each step, so there was less of a scalability factor. And really, part of the reason that I used this particular data set was to try and help show how scalable this application was.
What did you use for message passing? How did you go about it?
I used the message passing interface, but implemented with MPI for Python, or MPI for Py that is, and then the BSP module that I used comes from Scientific Python, and that can be built on either BSP lib or MPI for Python. So that's kind of either or.
How long was the program in terms of lines of code roughly to do everything that you did there?
Well, I think my whole program is about 200 lines, but that includes comments and white space, so it's probably only around 100, maybe.
Okay, thank you.
I just have a couple quick things. I just wanted to say thank you really quick to first Tash Bowler. He's the GX cluster administrator, and he helped me out a lot with installing a billion Python packages when I got it right and when I got it wrong. And then of course my mentor is Herb Schilling. He's right here in the front for you guys. He helped me out a lot, and he gave me a push towards working on parallel stuff. And I was kind of wary of that at first because it was a new area that I'd never really dabbled into. But I'm really glad that I did it because I really enjoyed it. And so thanks for coming. Thanks for watching.